In this question, we're asked to calculate the side lengths of a rectangular box that maximizes the volume if the total surface area of the box must be 1,000 centimeters squared. So this is a constrained optimization problem. We're trying to maximize a volume, and we're trying to maximize the volume with the fact that the total surface area of the box must be 1,000 centimeters squared. So this is a constrained optimization problem. So to get started, let's actually just draw the box. So we have something that's like maybe like this. So we have a box here. We'll call this X, this Y, and this side Z. And what we would like to do is we would like to figure out what X, Y, and Z should be in order to maximize the volume of the box, subject to the surface area being 1,000 centimeters squared. So what is the function we're trying to maximize? The function we're trying to maximize is the volume, which is X times Y times Z, X times Y times Z. And the constraint is that the surface area of the box must be 1,000 centimeters squared. So what is the surface area? The surface area is equal to, this face here of the box has an area of X times Z. And of course, there is another copy of this face on the back part of the box. And so the surface area from these two faces is 2 times XZ. The surface area of this side of the box is Z times Y. That's the surface area on this side of the box. On the other side of the box, there's an exact copy of that face. So together, those two faces have an area of 2 Y times Z. And of course, the top and the bottom each have a surface area of X times Y. So in total, the surface area is 2XZ plus 2YZ plus 2XY. And we would like that to be equal to 1,000. So I'm going to let this be my function g of x, y, and z. And I'd like that to be equal to 1,000. And this is my function f of x, y, z. So this is the function I'm trying to maximize. And this is my constraint. So I can write, I can make the function capital F of x, y, z. And it is equal to my function that I'm trying to maximize, which is x, y, z minus lambda times the constraint, which is 2xz plus 2yz plus 2xy minus 1,000. And now I set up my Lagrange equations by taking the partial derivative of this capital F function with respect to each of the variables. So the partial derivative of capital F with respect to x is yz minus 2 lambda z minus 2 lambda y. And the partial derivative of f with respect to y is equal to xz minus 2 lambda x minus 2 lambda z. And the partial derivative of f with respect to z is xy minus 2 lambda x minus 2 lambda y. And finally, the partial derivative of f with respect to lambda is equal to 2xz plus 2yz plus 2xy minus 1,000, all with a negative sign in front of it. Okay, and setting up the Lagrange equations, what we would like to do is we would like to make each of these partial derivatives equal to 0. So we set them all equal to 0. And that will give me a system of 4 equations and 4 unknowns. So the 4 equations will be, if I take this first equation here, I have that yz is equal to 2 lambda z plus 2 lambda y. The second equation here is that xz is equal to 2 lambda x plus 2 lambda z. And the third equation here is xy is equal to 2 lambda x plus 2 lambda y. And finally, this last equation here, after rearranging it a little bit, what I can find is that I have xz plus yz plus xy is equal to 500. Okay, so these are my 4 equations and 4 unknowns, so I'm going to label them. This is equation 1, this is equation 2, this is equation 3, and this is equation 4. Okay, So from equation 1, I'm sure there's many ways to solve these four equations. Oops, I guess this is not equation 3 again, this is equation 4. There are probably multiple ways to solve these equations, but I'm just going to choose this one. So I'm going to take the first equation and divide it by yz. So from equation 1, I get that if I divide equation 1 by yz, I get 1 is equal to 2 lambda over y plus 2 lambda over z. The reason I get that is dividing the left-hand side by yz. Yz divided by yz, of course, is 1. And if I divide this term by yz, the z's cancel out, and I have 2 lambda over y. And this term, when I divide by yz, I get 2 lambda over z, because the y's cancel out. Okay, so I have that equation. And say I do the same thing, or a similar thing, to equation 2. What do I get? I'm going to divide equation 2 by xz. So that gives me xz divided by xz is just 1. This term divided by xz is 2 lambda over z, because the x's cancel out. Plus, if I divide this term by 2 lambda z, or sorry, if I divide 2 lambda z by xz, what I end up with is 2 lambda over x. Okay, so I'm going to call these two equations, this is going to be equation, say, 5 and 6. And so if I equate, so equation 5 has 1 is equal to this, and equation 6 has 1 is equal to the right-hand side here. So I can equate these two equations, equating equation 5 and 6 gives me that, okay, I'll separate this. It gives me that 2 lambda over y is equal to, nope, not quite, 2 lambda over y plus 2 lambda over z is equal to 2 lambda over z plus 2 lambda over x. Because both of these things equal 1, so obviously they equal each other. And I see here on the left-hand side I have a 2 lambda over z and a 2 lambda over z. So I'm left with 2 lambda over y is equal to 2 lambda over x. Of course, I can cancel both sides with the 2 lambda, so 2 lambda and 2 lambda. And what I'm left with is that 1 over y is 1 over x, which means x is equal to y. Okay, so know that x is equal to y. So I can take equation 3 here, and from equation 3, if I divide both sides of equation 3 by xy, from equation 3, I'm going to divide both sides by xy, similar to what I did above, and I get 1 is equal to 2 lambda over y plus 2 lambda over x. This will be equation 7. Okay, so I'm just going to square this, because that's one thing. From equation 7, let me see, I'm going to equate equation, say, equating equation 7 and say equation 6. That gives me that 2 lambda over z plus 2 lambda over x is equal to 2 lambda over y plus 2 lambda over x. The 2 lambda over x's cancel, so do the 2 lambdas on top here, 2 lambda and 2 lambda. And what I end up with is that 1 over z must be equal to 1 over y, which means that 1 over z is equal to 1 over y, which means that y is equal to z. So I have x is equal to y is equal to z, so all three of these sides are the same length, which means we have a cube, so all three of these sides are the same length. And so let's just say that x is equal to length L, y is also equal to length L, and z is equal to length L. And so the only thing that remains is us to figure out what L actually is. So we can go up here into equation 4. From equation 4, we have that all of these terms are just L's. So this is L times L plus L times L plus L times L. So this gives me 3L squared is equal to 500, which means that L squared is equal to 500 over 3. And thus L is equal to positive or negative the square root of 500 over 3. And of course we reject the negative version because it doesn't make any sense to have a negative length. And so we conclude that the volume is maximized when x equals y equals z is equal to the square root of 500 over 3.